Now in this problem, we have a spring that is at the x equals 0 position. It's not compressed, it's not extended. It's on a horizontal frictionless surface, and at one end it's anchored onto a wall. The spring has a length of 18 centimeters as it's relaxed. The spring constant, 420 newtons per meter. There is a 300-gram mass that someone is going to push against the spring until this mass and the end of the spring is now 12 centimeters from the wall. So we're compressing the spring. The system's released, and this mass then is going to be pushed by the spring back to the right. We compress to the left. The spring pushes back to the right. And when the mass is 18 centimeters from the wall, it collides and sticks onto another 300-gram mass. So there's a collision involved. In the collision, it's inelastic, and 50% of the kinetic energy is lost. The two masses are sliding now up a 25-degree frictionless incline until the masses stop. We want to determine the position of the masses along the incline. Well, this is a conservation of energy problem. It's not a kinematic problem. The spring, as it extends, the force is not constant. So the acceleration will not be constant. So we don't want to use the kinematic equations. We'll use energy principles. So make a little sketch, a little artwork here that gives the concept. Here's our target mass that'll be hit. Here's the mass we're going to push against the spring. 18 centimeters, spring is relaxed at this time. We push to the left 6 centimeters. Spring is compressed. Then it's going to come back here, collide here. These two stick together and travel up this ramp at an incline of 25 degrees. So energy problem, we need to calculate some energies. We're going to have the potential energy of the spring become kinetic energy of the object here at this equilibrium point at the x equals 0 point. I could even label that here. So we have potential energy. When the spring is compressed, the spring extends back to the right, and that potential energy is converted to kinetic energy. There's no friction along the surface, so all the potential energy will become kinetic energy right before the collision. The potential energy is 1/2 kx squared. That's how we calculate potential energy for the spring. It's being converted into kinetic energy, 1/2 mv squared. So put in some numbers here. The 1/2 kx squared. 420 is the force constant for the spring. We pressed back 6 centimeters. Our object is 12 centimeters from the wall at the full compression. We started 18 centimeters from the wall, so the proper number for x is 0.06 meters to stay in standard metric units. It's not 12. It's not 0.12. But the spring has been compressed 6 centimeters. If you, and you should, do this calculation yourself, you come up with 0.756 joules. That's the potential energy that the spring has before it's released. So we come to the collision. This now all becomes kinetic energy before the collision. At the collision, 50% of the kinetic energy is lost, and 50% remains in the two objects. So half of this number is 0.378 joules, and that is kinetic energy carried by the two masses as they then they move on, and they move up the ramp. On the ramp, the kinetic energy of the objects is now converted into potential energy. When we're at our largest distance up the ramp, the object will be stopped, and we have no kinetic at that point. It's just potential energy, and that will be calculated using mgh, where h is our vertical height that we've gone up from this horizontal surface. So 0.378 joules, that's kinetic energy. mgh, we have two 300-gram masses, so 0.6 kilograms. Each mass is 0.3 kilograms. There are two of them. G is 9.8 meters per second squared, and H's are unknown. So you can use your calculator. I came up with 0.0643 meters, 6.43 centimeters. Now we're in a little triangle here, and we really want to know x. How far along the incline did these objects move? we have h that's opposite to this 25-degree angle. The sine of 25 degrees is equal to the opposite side divided by the hypotenuse. So cross multiply here. X is equal to 0.0643 divided by sine of 25 degrees. I came up with 0.152 meters. 15.2 meters is the position now of the two masses up along the incline. Again, we use conservation of energy principle here. We did not try to use the kinematic equations because the spring force is variable as the spring extends back to the right, and the acceleration is variable. So we can't use the kinematic equations. We use energy principles. And again, we used energy on the ramp. There's no friction to worry about of creating a work by a non-conservative force. That on the ramp, the kinetic energy of the two objects at the bottom of the ramp becomes all potential energy as the object reaches its maximum height. Well, if you have questions, ask your instructor. If you'd like to see other physics and astronomy videos, welcome to visit those two websites. They're free. Listing of the videos with the title, the time in minutes for the video, and a short description of what the content of the video is. Nothing to buy there, no registration. Just make use of them. Hopefully it'll be useful. And if you do find these videos, I appreciate it if you'd subscribe to my YouTube channel.